Howdy folks, welcome to the first checkpoint in this computational linear algebra series. These checkpoints are designed to just be quick opportunities to summarize and review what we've covered up until this checkpoint in the series, because we are going to be either talking about very different topics or topics that will require really good understanding of the previous material covered. So if you are watching this through in the playlist, this is a good time to sit and reflect and make sure you have a good understanding of what's going on before you move on to other things. So the first episode in this series is just on linear systems, and it was meant to just show you that we can solve an AX equals B system computationally. It was also meant to show you how quick we can do it and how quick we can do it for large systems that you wouldn't want to do by hand, okay? And this really shows us the utility of being able to use modern computation in studying and in gaining better understanding of linear algebra. But what this hopefully also showed you is that there are many actual applications of linear algebra that you will see later on in the series as we kind of go through things. Now, the second, third, and fourth episodes are all kind of grouped together in that they have one goal in showing you how an AX equals B system is actually solved on the back end. So in episode 1, we showed you I showed you that you can solve an AX equals B system computationally with Python and Octave, but each one of these is one step in the entire process of how that back-end procedure actually takes place. So the second episode was particularly on triangular matrices, which are common matrix configurations that we've seen a lot since episode 2, and that you'll continue to see as we move into matrix decompositions of square matrices. And I also showed you that it's quite simple to solve triangular systems just based on the configuration of them, and that's really what gives them a good bit of utility. Episode 3 is on the forward and backward substitution algorithms, which are specific algorithms that allow us to solve either lower or upper triangular systems. We use forward substitution for a lower triangular system and backward substitution for an upper triangular system. We only covered the backward substitution algorithm in examples, and forward substitution was left as an exercise for you. I think it's an excellent exercise, and it's not too difficult to do once you have the backward substitution algorithm figured out. And I've given you all that code. I've actually given you all the code for all these episodes. It's available on my GitHub or GitLab pages linked down below, and you can check out all the code there for you. Episode 4 is on structured Gaussian elimination, which shows us how we can convert an A matrix into an upper triangular matrix. Not just the matrices themselves, though, but the entire system. So we're converting AX equals B into UX equals C. Then we have an upper triangular system, so we can use our back substitution algorithm, which will allow us to get the solution to that particular system. And that's where this is particularly useful, because after this episode, you should see the entire back-end procedure of how we solve for the X vector in AX equals B for any AX equals B system that we put into the computer. Now, I want to mention that we've only been considering square matrices. Non-square matrices will be an entirely different discussion after we cover matrix decompositions and some of the different matrix decompositions, because I think it'll be easier to better understand those matrix decompositions. And speaking of matrix decompositions, episode 5 was on the Liu decomposition. This is meant to just be an introduction to the matrix decompositions that we're going to get more in depth into. And this is more of a specific look, though, at the Liu decomposition, which is a very simple, common matrix decomposition that's used all the time, and actually it utilizes the really great configurations that we talked about in episode 2, the lower and upper triangular matrices. The more important thing, though, is that we use this to show why a solution obtained to UX equals C satisfies AX equals B, or at least I took you about 80, maybe 90% of the way and left the computational proof something for you to do for yourself. I think that's a great exercise. I think that's something that you should do. But this particular episode will also be part of the second checkpoint, since we're going to be talking a little bit more about more matrix decompositions. But this is really important because you can actually see an application of the matrix decomposition in doing that mathematical proof. This is still math related. This is not meant to be computer science or computer programming. This is meant to be the math behind how this actually works, with more of a focus on the computation side of things. So this is really useful, and this is really important, and you'll see those use cases once we start talking about more applications of linear algebra in the future, with data compression, image processing, and even machine learning or AI. So this is a great opportunity for you to ask any questions. If you're concerned or if you're unsure of what's going on, leave those comments, and I will do my best to answer them as best as I can. But in episodes 6, 7, 8, and maybe even 9, we will be discussing matrix decompositions, so gear up for that.